Morning. Morning, everyone. I'd like to thank George for his introduction, and also I'd like to thank him for his invitation to actually come and talk to you today. As he said, I am the Director of Earth Observation and Science of a company in Surrey, England, that was created in about 1985 as part of the University of Surrey. So we started as a small university startup in a little corner of a lab in a building that belonged to the university. From then on, we went on to become a commercial company, and since then we have actually been doing small satellites now for about 33, 34 years. We are now owned by Airbus, but we are still an independent company. I started working with the company about 17 years ago, 18 years ago, after working here in Portugal, actually on the space program here in Portugal, the then starting space program. Our marketing guys like this graphic quite a lot. They like this view graph. It's quite busy. The only thing I would actually call your attention to is the number of satellites that you can see there on the right, 43. This is the number of satellites we have built over the years, launched and operated, both for ourselves and for our customers. So we have a very varied customer base, and we work with them throughout the years, and we build not just satellites, but we also build relationships over the years with them. So we have also developed several space agencies. We have actually also supported them in setting up new companies, new startups all over the world. But what I'd like to talk to you today about is not so much the company. That's not what I'm here to do, but talk to you a little bit about small satellites. We are in a very exciting period of the space industry right now. So we are moving away from building very large spacecraft into constellations of small spacecraft. I usually call these the power of many. And that is quite a change from what has been happening until now. So companies like ours and university groups all over the world and other companies have actually been doing small satellites now for 30 years. But until now, they were always a niche market. They were always something that a few people, a few special people, I would say, in the words of some of the more serious developers of spacecraft, used to do in small garages and in small labs all over the world. But it is changing. And what I'd like to talk to you a little bit about today is how it is changing and why it is changing. And also where are the roots of this change and where do we think this is going to. So I call this challenging the traditional view. And this is a bit of history. Forgive me to start a few years back, but when we started the space era, let's call it, 1957, roughly, with the launch of Sputnik, we started by working in a very agency-based system. So agencies, big agencies like NASA and other space agencies were usually the drivers of these space era. But very quickly, we started to become dependent on satellites and space to monitor the Earth, to monitor our world, the environment, our weather, but also for communications. Many of you have probably today have used already some space technology without even noticing. When you actually use your sat-nav, the obvious one, but also when you are actually going to ATM machines and the timing of many of those machines tends to be GPS enabled. If you are using maps, nowadays they are probably done automatically from spacecraft photography images. Unlike what you would have in the old days where someone would go and measure things, nowadays you don't do maps like that anymore. You take a satellite image and then you actually convert that into a map. So the use of space technology is actually quite widespread these days. But until recently, until a few years ago, it was still very much very much limited to countries with big budgets. Even Europe had to actually pull together and join together several countries in the European Space Agency to actually be able to pursue these kind of activities, because they are quite expensive. It is quite an expensive proposition to go and launch 8-10 satellites. But this only happens if you actually start from the idea that satellites are expensive. if you believe that your satellites have to be expensive or that they are expensive to start with, you actually have a problem, because when you go and ask for a lot of money from your government, or when you go and ask for a lot of money from companies, you actually have to ensure that these companies, that you have lots of users, because that's how you justify those investments. They're big investments. So you have to have lots of people that say, I want to use that satellite. And what this has led is, over the years, you start getting satellites that are actually very complex, because they have to be able to actually do many things. So they have to satisfy the military user, they have to satisfy the civilian user, they have to satisfy the Ministry of Agriculture, the Ministry of the Environment, and they have to do lots of things at the same time. When you do that, you make your satellites very complex. And when you make satellites complex, you actually take a lot of time to design them, you take a lot of time to test them, and all this costs money. I usually say that materials are probably the least expensive thing in a satellite. Labor, people are the things that cost money. So if you take a long time to build them, and if you take a long time to test them and integrate them, satellites will be expensive. And if satellites are expensive, you can't build many, you build few. If you build few satellites, you launch them occasionally. So they're always bespoke systems. They're always custom-made. And if they're always custom-made, they are even more expensive, because next time you are going to have to do that all over again. And this creates a vicious circle that for many years has prevented us from actually having a widespread application of space outside a core set of applications. One example, probably the pinnacle of the example of this continuous increase in cost, is this satellite, Envisat, European Space Agency satellite. By the way, before I say, this is a great mission. I've known people that worked on these. As a satellite, was a great spacecraft. But it was 8 tons, you can see the size of it, cost a lot to build, took a long time, and in reality, it was a compromise, because all those boxes that you see on the spacecraft, they are different experiments, they were different instruments, and they all had to work together, and they all had to be compromised so that you could actually build this spacecraft. Because what you had is everyone, well, I want my experiment, I want my instrument there, and then in reality, what you end up is with a mishmash that is not really good for anyone. It's a little bit good for lots of people, but it's not perfect, it's not optimized. So, a bit of history, as I said. At some point, in the late 70s, a group of people started to actually work in a different way. They started questioning this way of working. They said to themselves, we want to work in space. And because we want to work in space, we want to actually work without these shackles, without these big budgets. They wanted to do things in a different way. The gentleman that you see on the middle there, the shorter gentleman, in a very dubious fashion statement, is actually my boss, Sir Martin Sweeting, and this is when he was a lecturer at the University of Surrey. He's still a professor, but at this time he was a lecturer of electronics. And he was a specialist in telecommunications, and he enjoyed that. And because of that, his hobby was actually space and electronics and radio communications. So in around 1978, that's when that picture there was taken, he and a few other lecturers at university built a little ground station that could receive amateur radio satellites, but also some meteorological satellites. The objective was just to try something. And from there, together with the rest of the community, the AM community, the amateur radio community that had been building these things, small satellites, amateur satellites for a few years by then, they started slowly changing the way people think about space. So this was a different kind of group. They thought in different ways from the rest of the space industry at the time. So you see there Martin again, in 1984, working on his second satellite. This was a small satellite built at the university, 50 kilos, and it was already quite a sophisticated satellite. By the way, that still works. It's now in orbit, has now been in orbit for about 31 years. And you can still use it occasionally. But the main thing was, it wasn't just about making cheaper satellites or different satellites, but there was a philosophy. And there was a view that if you wanted to make space accessible to everyone, you actually have to change the way you thought about space. And so the way they actually started thinking about space is about keep it small, make spacecraft faster, use normal electronic components, for instance. I'll talk a little bit more about that. And build and launch quickly so that you can actually launch many. And if you do that, you actually build an heritage of systems. So next time you are going to build another one, rather than developing a new design, you just build exactly the same thing you built before with a small change here and there to improve it with a different payload. And that makes it much simpler, cheaper, and faster and quicker to build satellites. And that was quite an important change in the mindset. So if you do this, if rather than starting from the idea that satellites are inherently expensive, you start by, I can make a low-cost satellite, then it's much easier to actually pay for the satellite with one user. So one user group, one person that is actually going to say, okay, I have an application, I want to use it, I want to use the satellite. And if you do that, you also can focus on a small number of applications. So that, of course, makes your satellite simpler. It's less complex. It's much more optimized, it's much easier to optimize. This is how you make your 50-kilo spacecraft. And if you do that, you actually can build them quickly, and you can launch them more frequently. And if you launch them more frequently, you actually start reducing the price of satellites because you are reusing designs, you are actually bringing down the cost of design and the cost of actually building satellites. So you are then in a virtuous cycle or circle. This is where the industry has been going in the last few years. And it's not even bigger companies like Boeing or Lockheed are now looking at this kind of application. They are going through these cycles. And when you start doing this, you can do something like this. A few years ago, in 2008, we launched the Constellation together with a Canadian company and also for a German customer of 5 satellites. And they were built in about 4 years. They're still operating. They're a commercial system. They take images. And they are actually quite complex machines, and they are actually very useful from a point of view of actually for agriculture, for environment, and they are being used daily. And these 5 satellites costed about 150 million. And this includes everything, ground segment, includes actually all the launch and building of the satellites. But you can only really do this if you have small satellites. And the advantage and low cost. And the advantage of having 5 spacecraft is that you then use them together. So rather than having one satellite that comes over every other time, you actually start using these together. And so you get much more out of it. Now, there is of course a question that you might ask. Is how do you make small satellites low cost, or any satellite low cost? It is not obvious. Although I said that, okay, there is a process that you start. You can have your virtuous circle. The reality is that you have to start from low cost. That is the seed. And then from that, you can actually start bringing the cost down even further. So I'll start with something that probably you know a lot more than I do about. And this is about components. So one of the first things that people like Martin and other pioneers did was actually looking at, can we use commercial off-the-shelf components in space? Traditionally, the space industry used subsystems and units that were built up of high reliability components. Space-rated is the expression that is normally used. That is also it's a synonym for expensive. It costed a lot. Now, there were good reasons for doing this, because when you didn't know exactly how components behaved in space, you were careful. But the reality is that was driving costs. That was driving the design of spacecraft to a level, to a point where actually there was no point in trying to cut costs because the components costed so much. So somewhere in the 1990s, people started predicting that commercial unscreened components, so the integrated circuits, the active, the FET that we use every day on terrestrial applications, would start to reach a level of reliability similar to the screened parts that were being used for space. And these started to say to us and to the rest of the industry that actually COTS components were probably going to be okay. And the reality is that they have reached a similar level of reliability. In our experience nowadays, many of the terrestrial components are actually better than a lot of what you buy space-rated. We see more problems in space-rated components in percentage in relation to the levels we use on our spacecraft than we see on commercial off-the-shelf. So, looking at that, we started using them. And we started using them a lot. And by doing that, we built a lot of knowledge. One of the things that, for instance, everyone was very scared about of using commercial components in space was radiation. Space environment it's not nice. There's a lot of radiation around, there are lots of particles, cosmic rays, and all of these actually damage our circuits. But one thing we noticed is actually it's not that bad, it's manageable. Of course, you can't just pick up a component and say, oh, well, I'm flying it, without actually thinking a little bit about it. But if you know the families, if you know the technologies that were used to produce it, if you actually know a little bit about what other people are doing with that component, you can actually get a lot of information and confidence that it will work in space. And then we also started doing another thing, that is, we started measuring our own radiation environment. So our spacecraft, they all carry radiation monitors. Not all, but the majority, actually. And that is important because that allowed us to build a direct knowledge of the space environment, rather than relying on pessimistic models and models of systems, things that were not really designed to be operational. They were more designed by scientists, of which I am one of them. It's one of the things I used to like was space environment. But they were not really designed to answer a question that was, for a commercial application, can we actually use these components? Can we use these in space? So we built that body of knowledge. And nowadays we have got a large database of parts that we have used in space. We know how they behave. We understand how the families work in space. And this has allowed us to actually continue to use commercial off-the-shelf components. And what you see in there is an example of that. Those are two subsystems. Actually, they are solid-state data recorders. So this is something we started using a few years ago. So this is from 2002, now about 12, 13 years ago. In reality, we have actually evolved a lot from these, but this is a good example of how you actually how you can use COTS in space, but also how you have to be smart about it. So if you see that little cross brace, aluminium cross brace in the middle, underneath there is a PowerPC processor. Now, that's a commercial, off-the-shelf, terrestrial application. I believe it's an industrial rated component. But it works perfectly in space. But you have to be careful with a couple things. There are two things that you have to think about. One is vibration. When you put satellites in a rocket, they vibrate, they shake. And things don't like that. Many components don't like that. So we have to be a bit careful. So you put a brace, you put a mechanical brace, and that solves that problem. And then also because there is no air, it's very difficult to actually cool things in space. So then you'll see that there is a little copper bracket that is underneath that cross brace and goes to the wall of the box. And that actually is used to actually dissipate the heat. So that's actually how you get rid of the heat that process is going to produce. It's a fairly powerful unit. And this is this kind of thinking that actually you have to apply. So if you are careful with that, you can actually fly these components in space. This is not to say that occasionally you don't have surprises. Single event latch-ups are a big problem for the space industry. So that's when radiation particle, cosmic rays usually, or protons, hit your active component, and they generate basically a short circuit inside that component. And that is a big problem for the industry. But if you are careful, you can actually you can design some protection measures. So you can have switches, fast switches that switch off your board if you detect a high current event. And sometimes you can use special components that are actually SEL immune. They work, but you do sometimes have surprises. And for that, you have to actually be careful the way you actually fly these systems. So what we do is we usually fly old with new. So if we've got a new design, we will actually fly it together with some of the old designs, because at least if the new design fails, we can always go back to the old design. And all these measures, all these ways of working have been evolving over many years. And now they are actually allowing us to do a commercial business with small satellites. And occasionally, you have to be careful. There are certain things that you cannot try to actually just use commercial off-the-shelf components. This thing is an antenna pointing mechanism. This is a critical element of many of our satellites. It allows us to actually use a high-gain antenna pointing at the ground station. And to do this, we actually use very much components that are not just commercial off-the-shelf. Some of these components are actually space-rated. And this is because when it comes to mechanical work, that's actually difficult to not use those kind of components. Many of the parts, they have wear issues. They actually will suffer over the years. So you have to be a lot more careful when you are talking about mechanical systems. That system we designed in-house because when we looked for commercial systems, they costed about $2 million. And we said, no, we can't afford that. So we actually designed that in-house. They cost about a tenth of that. So it can be done, but that system actually has been tested, qualified, and it uses parts that are not commercial off the shelf in many of its mechanical aspects. And as I said, this is not just about, but it's not about just components. It's not just about using low-cost electronics. It's actually also about thinking. And how do you do it? There is an old philosophy, if you want to call it that, that makes a difference. And I give you an example of what is our engineering process. And many other people follow a similar engineering process. And this is all about starting with the existing designs. Manage changes and risks. Don't be afraid of risk and change. And this is something that the space industry is not usually, the traditional space industry is not very good with. They usually are very conservative. Now, we like that. We like to change. We like to manage the risk. And usually, it works. And then, it's also about verifying against requirements, but trying to verify at the higher level possible. The way we like to test our satellites is not by testing every individual box, but put it all together and test it as a system. Because that actually proves that it works as a system, proves that the individual components are working. So, if you think about it this way, and then you use COTS components, you are a long way into making things cheaper. Your low-cost satellites. But then you also have to do another thing, that is, you have to evolve. I've got two examples. These satellites are very similar. They were actually designed to do exactly the same thing. This is a wide area imaging system. And they are about 7 years apart in terms of design. And you can see that the numbers are growing very fast. The numbers are picking up. And actually, on these satellites, we didn't even stretch ourselves. This was just using what we needed. In reality, if you look at nowadays, on that graph, so on the top, by using new electronics, by using new solid-state memories, new flash memories, we are actually now at a point where we are starting to grow, I would say almost exponentially in terms of storage on board. So next year, or in 2 years' time, we'll be doing the 1 terabyte storage on board. At the same time, the downlink rate, this is a big measure for us. When we are downlinking data, how fast can we downlink the data? So when we started in the early 2000s, using what we call then our high data rate downlinks, we were doing 8 megabits per second. Right now, I'm about to launch 3 satellites that will do 500 megabits per second each. And you can actually double that to 1 gigabit per second. And in a few years' time, we are going to be 1 gigabit and above that. So there is a growth. And the growth actually comes from advances in electronics. It's not, we are just using what the electronics industry is producing. And by doing that, we are actually being able to incorporate, because we use COTS components, we are able to incorporate much earlier the new advances. So when a new memory comes out, we can actually start flying it immediately. Traditionally, in the old space approach, no, you would have to actually prove that that thing worked, and so you'd be several years ahead of away of using that component. Because we can use it much quicker, we can actually do it much faster. Now, I've talked a little bit about how you lower the cost of satellite. One thing that some of you might ask is, who cares? Why do we actually want low-cost satellites? What does that make? NASA and ESA and the Russian Space Agency and the Chinese Space Agency have been doing expensive satellites for many years. They're happy, and everyone is happy, and we get our information, we get our GPS, and we get our Galileo, or we'll get our Galileo. So, what, eventually? So, what actually, why does it matter? And I'm just going to give a few examples, and this is going to be the end of my presentation. Why it is important to do this. I call it the power of many. Because one of the reasons people started doing lower cost satellites originally was just because then more countries, more institutions, more companies could have satellites. But in reality, what we started seeing is that the value of low cost comes not from flying single satellites, because single satellites will always be limited by physics. This is a nice picture of Dubai. You can see the Burj Khalifa in there, the tallest building in the world. Great picture. And you can take these, and there are several satellites that will take these pictures. But in reality, they will be able to take one of these pictures every 3 days probably, or every 2 days at best. So that means that if you are actually trying to monitor something continuously, or at least every day, you are going to be limited immediately because of physics. This has to do with orbital dynamics. The same thing applies to many scientific satellites, not just imaging satellites. And also a lot of this applies to communication satellites. If you don't want to go to the geostationary satellites, that sit at 35,000 kilometers altitude and are quite expensive, and it's quite expensive to get there, you need an awful lot of satellites to cover the entire Earth. And this is what companies like Iridium tried to do many years ago and succeeded. But they needed about 66, originally 66 satellites to actually, on a low Earth orbit that is much cheaper to get to, they needed an awful lot of satellites to do that. And this is why low cost matters. Because I usually give this example to people. I live in the UK. It's a great place to live, but if you like sunshine, you usually have to go somewhere else. So that image is 1 month of cloud cover over the UK. If you pay attention, there will be 2 days where there are no clouds. Most of the time, countries like the UK are cloudy. And this means that if you are trying to monitor the crops, for instance, using satellites, you have a problem. Because with more classical, with one satellite, this is a mosaic taken from pictures from Landsat. Landsat is one of the pioneer large missions for Earth observation. It's a US mission, very successful, but it takes images of that size. So you see those little squares. Each one is one image. And the problem is that it takes 16 days to go back to the same place because of the way the orbit works. So it takes one row of those, or one column of those pictures when it comes over, and then to go over the same place again, it will take about 16 days. This means that that mosaic, because of cloud cover, because, okay, you come over today and it's cloudy and you have to come over 16 days later, there is high probability that will also be cloudy. It took about a year to take that picture. So by then, your crops will have died. If you are monitoring crops, if you are trying to actually see, are my crops good, you can't use these techniques. You can't just rely on these satellites. So what you need is a lot of satellites that come over every day. And so those 2 days a month when you actually have cloud-free skies, you can take a picture. And this is what we did. So we built, together with many of our customers, we built a constellation called the DMC several years ago. And when we did that, it was 5 satellites, and every day they would come over the UK. And every day they would take a picture. And so on those 2 days a month, without cloud, you take a picture. And on those 2 days, you actually get your information. So it means that at least twice a month, you can actually monitor your crops. And who says crops, says forests, says a lot of other things. For instance, this constellation was used quite successfully to actually measure deforestation in the Amazon forest. And you can't do this with a single spacecraft. It's very difficult. because it takes a long time to actually image the entire of the Amazon forest because of cloud. But if you've got a large constellation or a medium-sized constellation of satellites, you can go over every day and you can start making these maps. So this is why it matters to have low-cost satellites, because you can't do these with very big, expensive satellites. You need lots of them. And nowadays, we are starting to look at constellations of not 5 satellites, but we are looking at constellations of 50 satellites for Earth observation, so that you can actually do high-resolution imaging every day, or every other day, of most places on Earth. And this starts to become quite important, because many of our applications are depending on this. Farming, using precision farming from satellite images can increase your yields by about 5 to 10%. When we are actually struggling to produce enough food for everyone, this is quite an important increase in our production. If we can actually go for developing countries and support them in improving the quantity of food they produce, that is going to be good for everyone. So, but it's not just about Earth observation, pure imaging, also meteorology. We are building a constellation right now of 6 satellites to improve forecasting using radio occultation, GPS radio occultation. And this is something that is now starting to help us in prediction of typhoons, in prediction of freak weather patterns, and actually is improving the quality of life of people. But once again, you need lots of satellites. These applications require geometry that requires lots of satellites. And to do that, you actually need to build lots of satellites and launch them. So they need to be small, so that the launch is inexpensive. But they also need to be low cost, because if not, the investment becomes so big that no one can actually do it. So this is the reason. Constellations are performance multiplier. So you can nowadays, with constellations of satellites, small, low cost, do much more than you used to do with one single big satellite. And it's much more sustainable. If they are small, low cost, you can actually keep replenishing the constellations over the years, rather than having to go and find funding to build another EnviSat. So, of course, they can't do everything. You still need big satellites. Big satellites have a place and will continue to be built. But actually, for operational applications, probably small satellites are better now. And if you look particularly across the Atlantic into the US, there are an awful lot of new constellations appearing, and they are commercial in nature, because it's now cheap enough to build spacecraft for commercial applications. Small companies can start doing it. And this is a big change, and this is going to have a profound impact in the way that we actually use space. And one thing I would like to leave you with, one of the reasons I like this, I like Earth observation, is because I believe that we tend to care a lot more for things we know well. I haven't lived in this city for 17 years or 18 years, but I still care very much about this city, because it's my city, it's the one I know. When I drive around Lisbon, I understand this city. And this is because I know it well, I care about it. And actually, if we care a lot more about, if we know our world a lot more, we'll care more about it. When people saw the pictures from Apollo, the white, blue marble, it made a difference. People started believing that actually our world, we live in a planet that has finite resources. So actually being able to know our planet better, being able to monitor our planet better will only improve our ability to manage our planet, but it also make people care more about it. And this is one of the reasons I for instance, work in this sector. This is something I enjoy. And so this is why low-cost satellites are quite important for us. So I'll stop here. I hope it was enjoyable. I'll be here for the rest of the morning, so if you would like to ask any questions, we can probably talk a little bit outside. But I hope you enjoyed it. Thank you very much. Enjoy the rest of the conference.